All right, welcome back to Linear Algebra. In this first lecture of section 6.3, we're going to introduce something called the adjoint of a linear operator on an inner product space. We can start by recalling that we've already used this term adjoint applied to a matrix. So we can recall here in the notation that if you take a matrix over the complex numbers, in this case it's a square matrix, although you can make this definition for a non-square matrix as well, but it's adjoint, it's denoted by A star, is just the transpose of the matrix of complex conjugates. And you can conjugate the entries in the matrix and then transpose, or you can transpose and then conjugate, and you'll get the same thing. So in terms of matrix entries, if you like, if you take an I and a J somewhere between 1 and n, and you want to know what's the IJ entry of this matrix A star, well, you take the Ji entry of the matrix A, that's the transpose part, and you look at the complex conjugate of that. Okay, so that's what I mean by the adjoint of a matrix. Okay, so the goal of the lecture is, given a linear operator on an inner product space, finite dimensional inner product space, I'd like to define an operator also denoted with a star, T star. And if you like, we can kind of motivate this by saying, like, well, what do I want? If I take an orthonormal basis for my inner product space, I would like the matrix of this operator T star to be the adjoint of the matrix of the operator T. All right. Just a quick observation here that if you fix a vector y in our inner product space and define the map from V into the scalar field, sometimes maps like that are called linear functionals, but it's a map from V into the scalar field F. And how does it work? Well, for every X in V, I'll just define G sub Y of X to be the inner product of X and Y. I'm going to leave it as an exercise to you to show that that's linear. The linearity in the first coordinate of the dot product implies that that G is a linear map. It's somewhat surprising that in the case of a finite dimensional inner product space, every linear map from G into the scalar field has that form. So inner producting against a fixed Y is a linear map, and our first theorem says if V is finite dimensional, every linear map from V into F, it has that form. So here's the statement of it, theorem 6.8. So we got a finite dimensional inner product space called V, okay, usual notation for the inner product. And we're going to take a linear map from V into the scalar field F. So it's a linear transformation. Then there exists some vector Y, and it's in fact unique. There exists a unique vector Y, such that our linear functional G is just the inner product of X against Y. That is, G equals G sub Y, my notation above. So any linear map is equal to inner product against some fixed Y for a unique Y. Okay, proof of this thing is surprisingly straightforward with all the machinery that we've built up. Let's take an orthonormal basis for our inner product space and take G to be a linear map from V into F. And then here's how we can define the vector Y. You take G of each basis vector, Vi, take the complex conjugate of that, that's a scalar. Yeah, so it's an element of the complex number field. You multiply that by the corresponding basis vector Vi and add them up. That certainly gives us some element of V because it's a linear combination of the basis vectors. And then I just want to check that inner producting against that Y will recover our function G. Since everything is linear here, we can just check stuff on a basis. So if you pick a basis element, say Vj, a j somewhere between 1 and n, and you apply our map in the notation above, G sub Y of that thing, that's just inner product Vj with Y. Drop the definition of Y in there and then use the linearity of the inner product. I should be careful here. I'm using the additiveness of the inner product in the second coordinate. The scalar G of Vi bar comes out of that second coordinate conjugated. And of course, the conjugate of a conjugate is just the complex number. So that's just using the additivity and that sort of half linearness, the complex linearity in the second coordinate. But now we have an orthonormal basis. So in the sum, those inner products Vj and Vi are 0 unless I is equal to j, in which case that inner product is a 1. So all the terms in that sum vanish except for one of them when I is equal to j. So we just end up getting G of Vj. And since G sub Y and G are linear, if they agree on a basis, they're equal. Okay, so there's the existence part. There exists a y such that G is inner product, and we gave an explicit definition for what that y is. For uniqueness, if you suppose some other y has the property that inner producting against it equals Rg, well, then in particular, then for any x, the inner product of x and y and the inner product of x and y prime would be the same. So by that last part of theorem 6.1, those vectors y and y prime have to be the same. So that's the uniqueness. All right. So again, a linear map into the scalar field is usually called a linear functional. And what we just proved is in a finite dimensional inner product space, every linear functional is given by inner producting against a fixed y. All right. Here's just a super quick example. I chose this over the real field, so the complex conjugates are vestigial. But I'll leave it to you to check that the function on R2 that sends A1, A2 to 7A1 plus 11A2 is linear. I'll leave that to you. If we take the usual orthonormal basis for R2, the standard basis vectors E1 and E2, then the proof up above says let Y equal, well, you apply G to the first basis vector times E1 plus G to the second basis vector times E2. Again, the complex conjugates aren't here because these are real numbers. You can write them there if you want to, but they're themselves. You can work out the details that will give you the point in R2, 7, 11. Okay, so inner producting an arbitrary A1, A2 with 7, 11 with the usual inner product, 7A1 plus 11A2, that's exactly G of A1 times A2. So that just illustrates that theorem for this linear functional G. Okay, second and final theorem of this short lecture says the following, that we're going to ratchet this up to the adjoint map itself. So if you're given, again, a finite dimensional inner product space called V, and then let's take a linear operator on it. So T is a linear map from V to V. Then there exists a unique function, T star. It's also linear, so it's a linear operator. And it satisfies this kind of very special property, that for any x and y, the inner product of T of x with y is the same as the inner product of x with T star of y. Right? So that's this kind of defining property. Okay, so how to prove this? Well, given a y in V, let me define the function h sub y from V to f by h sub y of x is the inner product of t of x with y, not x with y, but t of x. So I claim that h of y is linear. And I'm going to give a kind of direct proof of that below, but an indirect proof of it, or sort of, it's also direct, it's sort of a shorter proof. If we think about what this function is, all I'm doing is taking the linear map T and composing it with the linear functional G sub y from above. Yeah, so I'm just going to take T of x first and then inner product that against y. So T and G are both linear, so their composition is linear. If you want to see a kind of computational direct proof of that, we can kind of go through the motions here. If you take two vectors in V and a scalar and just apply H to A times x1 plus x2, by the definition of H sub y, you plug that A times x1 plus x2 into T and inner product that with y. Okay, T is a linear map, so T applied to that business, you can push through and bring the scalar out. And then using the linearity in the first coordinate of the dot product, the scalar comes out and you can split that sum. And that's exactly A times the value of hy of x1 plus hy of x2. Okay, so h sub y is linear. It's linear for every y. So by the theorem we just proved, that h sub y is a linear map from V into F, there has to be some unique y prime such that h sub y is equal to just inner producting against y prime. So h sub y of x, which is the inner product of T of x with y, has to be the same as the inner product of x with y prime for some y prime, and it's unique. There's only one of them. Okay, so given a y, we found this unique y prime such that this inner product expression holds. All right, so that allows me to define a function. I'm going to define a function called T star, and T star's value at y is the y prime. That makes sense because y prime exists, and it's a function because y prime is unique given y. So that's what functions have to do, is given their input, they have to uniquely determine their output. All right. And by the way, we've cooked this up to where the equality in the statement of the theorem holds automatically. The inner product of tx with y is equal to the inner product of x with t star of y. It's by definition. It's by definition of t star. Okay, we got to show t star is linear. Got to show t star is linear. So let's pick a couple of vectors, call them y1 and y2, and a scalar called f. And then for any x, if we look at the inner product of x with t star of that linear combination, well, by the defining property above, you can move t across that comma, ditching the star. And now I'm going to use the complex linear, the conjugate linearity in the second coordinate of the inner product. Yeah. So I've got a sum over here. I'm going to split the inner product across that sum. This scalar multiple a, because it's in the second coordinate, it comes out with the complex conjugate on it. So I'm using that 1.5 linearness in the second coordinate. Okay, now I'm just going to move t back across the comma, putting a star on it. And then I move the a back into the second coordinate. So when you put that scalar back in, the conjugate comes off. Using the additivity again, we have that. And now comparing the first expression to the last expression, for any x, the inner product of x with t star of that linear combination is the same as the inner product of x with the linear combination of the t stars. So another application of theorem 6.1e says that those things have to be equal to each other, right? Two vectors that have the same inner product with x for every x are equal to each other. That's that theorem 6.1e, using it a lot here. Okay, so t star is linear. Okay, and then finally, we said that t star is the unique map that does this. So suppose you have some other linear operator called u from v to v that would also satisfy that the inner product of t of x with y is the inner product of x with u of y. It does that for every x and y in v. Okay, well, if u does that and t star does that, then we can get the equality, that the inner product of x with t star of y and the inner product of x with u of y are the same for every x. So yeah, you guessed it, another application of theorem 6.1a says that t star of y and u of y have to be the same for every y. So t star is equal to u. Okay, so t star is unique. That concludes the proof of that theorem. This map, T star from V to V, guaranteed, the unique map guaranteed in theorem 6.9, is called the adjoint of the map T. Okay, so we're going to use the same name for that thing that we defined for a matrix. In the next video lecture, we'll sort of see that names are compatible. So what does this adjoint map do? Well, for any two vectors x and y in our inner product space, it satisfies this equality about the inner product. I like to think of this as when you move t across the comma, you have to put the star on it. It becomes the adjoint, moving it across the comma from left to right, the way you're looking at it there. You can also do it right to left. If you looked at the inner product of x with t of y, you can flip those, paying for it with the conjugate, then move t across, because it's true for all x and y, and then flip them back. All right, so you can do this. If the t is on the left, you can move it over to the right, putting the star on it. And if the t is on the right, you can move it over to the left, put the star on it. All right, so this adjoint map is sort of an inner product preserving function that goes with t, but it sort of preserves the inner product in the way of the two equations that I just highlighted down there. That the inner product of t with another vector is the same as the t of x with another vector is the same as the inner product of x with t star of that other vector, and vice versa. Okay, we're going to call this one here. Thanks for listening.